Hi guys, so in this video I'm going to finally present the proof for the extreme value theorem. So yep, let's go ahead and see what the theorem says and let's write a proof for it. So the extreme value theorem states that suppose S is a subset of R to the power of n and S is a compact set, and f is a function that maps from the set S to the set of real numbers where f is a continuous function. If these conditions are satisfied, then the extreme value theorem states that there exist elements a and b in S such that for every x in S, f of a is less than or equal to f of x, which is less than or equal to f of b. So in other words, it's essentially saying that f of x has a maximum and a minimum value that occurs at points that lie in the set S. So first of all, let me give you a little bit of an idea about how we are going to go about proving the extreme value theorem, and then I'll come back to why this lemma that is relevant that we need to prove before we write out the proof. So the basic idea is this. We know that S is compact. What we are going to show is that the image of S under F is also compact. So if that is true, then you could say that the set f of x such that x is an element of S is also compact. And if this is compact, we know that it's bounded and we know it's closed. If as this is bounded, clearly it has an infimum and it has a supremum, and because it is closed, we know that the infimum and the supremum are elements of the set, and thus we basically proved the extreme value theorem. So that's basically the idea. Proving the extreme value theorem itself is quite simple. It's basically the bunch of lemmas that you have to go through in order to prove this theorem. So, I mean, pretty much every single video that I presented before this regarding the Bolzano-Weierstrass theorem will be relevant over here, because while we used part 1 and part 2 of the Bolzano-Weierstrass theorem to actually prove the Bolzano-Weierstrass theorem itself, and now I'm going to use that theorem in order to prove this lemma, and then I'll use this lemma to prove the extreme value theorem itself. So you can see that it's actually a pretty long progression. So yep, let's go ahead and see what this lemma says now. So I mean, the only thing that is missing over here is to show that f of s is also compact, and that is what the lemma says. It says that continuous functions map compact sets to compact sets. That is, if we assume that s is a compact subset of r to the power of n, and f is a continuous function that maps from s to r to r to the power of n, which is continuous everywhere, then the set f of x such that x is an element of s is also compact. Okay, I misspelled it over here. It's also compact. So yeah, let's first of all go ahead and prove the lemma. The lemma is actually quite simple to prove. So let's go ahead and begin with the proof of the lemma. So this is proof. So let me just first of all set everything up. Let's assume that S is a compact set of R to the power of n. Let S, which is a subset of R to the power of n, be a compact set. Let F be a function that maps from S to R to the power of n, be a continuous function, be a continuous function. I want to show, so here's what I want to show. I want to show that the set f of x, okay, I'm going to label this set something. So I'm going to say let this be s f of s. So f of s, which is equal to the set f of x, where x is an element of s, is compact. Is compact. Okay, so the first thing that I want to do is to emphasize that I'm actually not going to prove that this function is closed and bounded. Sorry, the image of S under F is closed and bounded. Instead, if you refer to the Bolzano-Weierstrass theorem, there is an equivalent definition of compactness, or in this case, sequential compactness, which says that if S is a subset of R to the power of n, then it is compact if and only if for every sequence in S, there exists a convergent subsequence whose limit lies in S. So that is the equivalent definition of compactness that I'm going to use in order to prove that the set f of S is also compact. So let's go ahead and begin the proof. So the first thing I'm going to do is I'm going to say as S or let the sequence A of n be a subset of S. Then by the Bolzano-Weierstrass theorem, so by the Bolzano-Weierstrass theorem, BWT, by the Bolzano-Weierstrass theorem, there exists a subsequence or a convergent subsequence, a convergent subsequence of A of n whose limit lies in S. And of course, this is only because S is compact by assumption. Let this subsequence be the sequence is of n's of j, and of course this is defined over j. And one other thing that I'm going to also assume is that this converges to some number. Let's say this converges to a. And okay, I guess a is fine. Oh, by the way, these are all vectors, and a be its limit. Okay, that is as j tends to infinity, a of n's of j tends to a. Next, then, and so first, now the next thing I'm going to do is, of course, I'm going to use the equivalent definition of compactness on the set f of S itself. So now I'm going to notice that since A of n is a sequence in S, it follows that f of A of n must be a sequence in f of S. Then it follows that f of A of n, that the sequence f of A of n, which is a sequence over n, is a subset of f of S, and importantly, the sequence f of A of n's of j is also a sequence in f of S, is a subsequence, and I'm just going to label this one, this one of 1. Okay, so now notice that the only thing I have to show is that f of A of n's of j converges, and that the limited converges to lies in the set f of S. If I'm able to show this, I've basically proven that the set that f of S is compact. Now, why have I proven that? Is because it's primarily because A of n, this sequence over here, A of n is basically was any arbitrary sequence in S, and then f of A of n is also any arbitrary sequence in f of S. So basically, the argument here holds for any arbitrary sequence in f of S. And I've shown that in other words, what I would have shown is that for any arbitrary sequence in f of S, there exists a convergent subsequence whose limit lies in f of S. And that is precisely what it means for a function to be compact by the Bolzano-Weierstrass theorem, or for a set to be compact by the Bolzano-Weierstrass theorem. Okay, so next, notice that as f is continuous, it follows that limit as j tends to infinity of f of a of n of j is equal to f of the limit as j tends to infinity of a of n of j. This we know is just f of a, and of course this is an element of s of f of s. Why? Because as a is an element of s. Okay, so this basically completes the proof, because f of a is of course the limit of the sequence f of a of n of j, and it lies in f of s, and thus by the Bolzano-Weierstrass theorem, or thus I would say thus, as a consequence of the Bolzano-Weierstrass theorem, f of s is compact. Okay, so one thing that I would like to emphasize over here, just because I don't want to leave, anything just completely unjustified. Although, I mean, if you were to write, if you have a test or if you have any analysis class, and I would like to stress high level analysis class. Then, if you write this proof out the way I've written, you wouldn't have any issues. However, for the sake of understanding, because that is the real purpose of making these videos, the idea is to understand why is it true. You need to justify this step, and it turns out that if f is continuous, this can be done. It cannot be done generally if f is discontinuous. Now I am going to leave this as an exercise for you to try on your own. The theorem is that if f is continuous and a of n is a sequence, then if a of n converges to a, then f of a of n will converge to f of a. That you can prove that very simply by using an epsilon delta argument. Okay, so now that we're done with the lemma, let's go ahead and write the proof of the extreme value theorem itself. So this completes the proof of the lemma, and now I'm going to write out the proof of the extreme value theorem. So now what I want to show that there exist vectors a and b in the set S such that for every x in the set S, f of a is less than or equal to f of x, which is less than or equal to f of b. Okay, so you can go ahead and write out a rigorous proof by taking a and b to be the infimum and the supremum respectively of the function f on the set S. Let x be any subset, let x be any element of S, and thus it follows, because f of a is the infimum and then f of b is the okay, one mistake I made when I said is take a and b to be the supremum and infimum. What I really meant is f of a to be the infimum and f of b to be the supremum. And then this inequality will hold because of the very fact that f of a are the supremum and f of b, f of a is the infimum and f of b is the supremum. One thing that you'll still have to show is that that a and b are in fact elements of S. So you can go ahead and write out, the step-by-step rigorous proof, or I'll basically just explain why this is true, and that should also be sufficient. So firstly, as S is compact, and because f is continuous, it follows that f of s is also compact by the lemma above. Thus, f of s is both closed and bounded. Is both closed and bounded. By the way, just something for you to think about. In the lemma, we proved that continuous functions map compact sets to compact sets. Is it also true that continuous functions map closed sets to closed sets, or bounded sets to bounded sets? See if you can figure that out on your own. Anyhow, so we've shown that the f of s is both closed and bounded. Then, uh, as f is bounded, it follows, or it's not the fact that f is bounded, f of s is bounded. It follows that the infimum, and so this is the infimum over the set S of f of s, or it should just be the infimum of f of s, because f of s is already a set. The infimum of f of s and the supremum of f of s are both real numbers. Pull this off this way. Additionally, or what I could say first is, then for every x in S, the infimum of f of s is less than or equal to f of x, which is less than or equal to the supremum of f of s. Lastly, as f of s is closed, it follows that both the infimum, so the infimum of f of s and the supremum of f of s are elements of the set f of s. In other words, there exist elements a and b in the set S such that f of a is equal to the infimum of f of s, and f of p is equal to the supremum of f of s. Thus, by construction, for every x in S, f of a is less than or equal to f of x, which is less than or equal to f of p, and that completes the proof of the extreme value theorem. So yeah, let me just summarize what we've done. So we started first with the nested interval theorem. We use the nested interval theorem in order to prove the fact that every bounded sequence in R has a convergent subsequence, and we generalize that result to R to the power of n. The next thing we did is we proved that if a point x or a vector x is in the closure of a set S, where S is a subset of R to the power of n, if and only if there is a sequence in S that converges to X. Now, we used these two previous theorems, in order to prove the Bolzano-Weierstrass theorem. We use the Bolzano-Weierstrass theorem to prove the lemma in this video, which basically states that continuous function map compact sets to compact sets. And then finally, we used this lemma in order to prove the extreme value theorem itself, which states that if f is a continuous function and S is a compact set, then f of S is also compact. And in particular, there exist elements A and B in the set S, such that for every x in S, f of A is less than or equal to f of x, which is less than or equal to f of B, and that completed the proof of the extreme value theorem. So the actual proof itself isn't that complicated. It's just that it's quite long, because there are a lot of lemmas and a lot of steps that you need to follow in order to write out this proof. But there is no proof, in this in the proof of the extreme value theorem that is technically difficult. So with this done, what I'm planning on doing next is proving the intermediate value theorem. For that, I'll need to prove some results about connected sets, which I'm going to do in the upcoming videos, and then eventually I'll write out the proof of the intermediate value theorem. So yeah, that's pretty much it for this video. I'll see you in the next video.